All right, in this lecture, we're going to be talking about how to exploit a particular class of bugs known as format string vulnerabilities. Now, these have been around for quite a while, dating back to the early 90s during some initial testing on a C shell program. One of the places where we saw the first actually attack using format strings was in the ProFTP daemon. This was a 1999 bug that was found, and essentially, what it boiled down to is that there was a path variable that the user was able to control that could be used to either as a local privilege escalation or potentially to gain remote access to the system. And these bugs became very popular in the early 2000s, and many papers and publications have been written about these since. So what is a format string? For those of you familiar with C, you've used these many times, but format strings basically enable us as programmers to display values in various formats very easily. So if you think about the problem that they're actually trying to solve, if you wanted to display a particular double value, $8.25, for example, and if every time if you had to write a lot of code to actually display just properly format it how you want to the screen, that would amount to a lot of code over and over again and lead to bugs. So format strings basically let us create a specification string where we have, using a certain syntax, indicate the type of variable to be substituted in and how we want the string formatted, and then the rest of the details are left to the particular string function. So if you just take a look at this example main program here, we have a number of different variable types. We have integers, doubles, chars, and then down below you can see print statements displaying those in different various formats. So the goal of the format string specifiers was to make life easy for programmers, but as we'll see, if not used carefully, can lead to a variety of exploits and attacks. So there are a whole slew of functions that take these format string specifiers. Here's the kind of the basic list that you'll see in standard C implementations. The most common formatters that you'll see, so the %C will basically indicates that you want to print out a character to the screen. %D is a decimal. E is signed notation, scientific notation. We have for floating points, octals, pointers, strings, and hex numbers. If you do a man page on printf or Google around, there's other less commonly used formatters as well, and other modifiers that you can read about. So from a vulnerability or attack perspective, what this really amounts to is that if the adversary, if the user can control the format string, then they're going to be able to exploit your system. So as an example, if we look at this program here, there's a string that we get from the user. Of course, this is also very vulnerable just by the fact that the gets function is used, but what's being used here is that the printf just prints the string that the user passes in. And so if you look down at the bottom of the screen here and you see the program run, well, what the user typed in, they actually typed a format string, the %D, in their string. So %D is for decimal. And so what you see actually printed out here is you have this big number, which you might be wondering what that is. Then is for decimal. So what's actually printing out here is this is a value from the stack, and in the next few slides you'll see exactly what that value is. So if we look at what the stack looks like when you make a printf call, you have at the top here you see a pointer to the format string, and so on the right side of the screen you'll see this is a snapshot from Ali debug. You'll see the format string that was entered, the %D is for decimal. Immediately following that, you have the actual format string. Then you have our save base pointer and return address. So the format string that's following that, those are the actual ASCII bytes for that format string. So if we think about, well, what is this 1763, etc. value? You'll notice that if we try typing %x for hex instead of D, you get a different value, hexadecimal value, but that hexadecimal value does not match the decimal value that we see above. Okay, so if we take a closer look at the stack, it does make sense, because essentially the 69207825 is taken as a parameter, right? So if you think about your format string, how this is normally set up, if you if you were in your program, you had %x for hex, you'd also have some variable that you wanted to print, right? So in this case, the number you see here, that's the actual parameter for the %x, and so it makes sense that there's a difference, because in the decimal string case, the data on the stack is going to be different, and so that's where you wind up with a different value being printed out. So there's a number of different consequences of these vulnerabilities, one of which is what's called a memory disclosure. And this is a serious vulnerability for a number of reasons. It can reveal sensitive data that the user isn't supposed to see. Memory disclosure vulnerabilities can also, especially in modern, newer operating systems where you have things like ASLR and other protection mechanisms in place, if you're able to leak an address in the program, that can help an attacker bypass ASLR. So in some of these newer protections, which we haven't talked much about those in this course so far, but these newer protections oftentimes require you to have multiple vulnerabilities in order to actually compromise the system. And so information disclosure can be used in those attacks. So in this case, what we're essentially happening, you see this string is a bunch of %x format specifiers, and so this is going to be printing out all these values that you see. So we see the output down below here, all the values that are on the stack, and at the very end, you're able to see what the actual return address is for this function. So in addition to the memory disclosure, you can also use these vulnerabilities to actually overwrite memory. And this capability comes from the %n formatting character. So the %n specifier is used to write the number of characters that have been printed so far to an integer pointer. So this gives us a 4-byte overwrite. Okay, so if you look at the code here and then the corresponding output below, you can see how the %n is used in practice, or legitimately used in practice. So here you're passing by reference the 3 integer parameters you see, and so those are going to get assigned a value that indicates how many characters have been printed. And so in this case we have 1 decimal point, so we have the value 1, 2, and then 3, of course, at the end, since we have 3 decimal points. And so to show the effects of this, and now we've looked at this screen and we've added a %n at the end, and what's being attempted here is an overwrite of the count of the characters that have been printed, which is in this case in ECX, sorting ECX, the hex 4D, there's an attempt to actually overwrite that 40116B value. And in this case, we're actually getting an access violation because we don't have write access to this that particular address. And so that just kind of goes to show you how you can kind of craft these to actually potentially gain execution by overwriting a return address or having that point to perhaps your shell code that you have somewhere in memory. So a few things to note about %n. It does continue counting. So if you have in a string, if you have multiple %n's, the count continues. And so our right values are ever increasing. It looks like the increasing here got chopped off by this image, but as you can see down below, we have in the first printf there's 2% ends, and then there's 2 decimal points, and so you can see how in I2 got a value of 2 instead of 1 because it's continuing to count after the first %n. In some implementations, there's also a H prefix that you can have, and that basically gives you a 2-byte override instead of a 4-byte. So if we look at this example, here we can see -1, so FFFFFF being overwritten with the FFFF0001. And so if you look down on the right, you can see the actual overwrite in the Ollie debug screen there. So a couple things that's important to know when you're thinking about or trying to craft a format string attack is that it's the number of characters that are printed that's our write value. So if we want to write an arbitrary value, we need to actually get those many characters printed in order to have the correct value write to screen. The second important thing is that the line parameter on the stack is our write address, right? So we need to also get to the right area in memory of where we actually want to write the value, which is the value is going to be the number of characters printed to that corresponding address. So some of the things, like most shellcode, and we talked in the previous lectures, keeping your string and your exploit string small, you want to save space. So space is always at a premium when you're talking about any kind of exploit. And so this slide just gives you some of the, shows you how many characters are being used. So %C, that's 2 format characters, how much memory, and then how much count do you get from as far as the %n is concerned. And so some of these have some risks, like at the end %s. This is going to, of course, this is going to read up to the first null byte, but the risk you run into is that if there, for whatever reason, isn't any null bytes, you could potentially continue reading all the way until you hit memory that you don't have read access to, and that would throw an access violation. So there's a few that you have to be concerned about potential crashes. So, but one of the good things about %s is that this can be used to disclose quite a bit of memory depending on the value that's in there. So you don't want to, you just want to be careful that you don't hit the end of the stack before you find this null terminator. And so, but in all likelihood, there's going to be a lot of null bytes on the stack, and so it's in all likelihood that this is not going to access violate if you just have one of these in there. That'd be fairly odd to be able to have a single %s and then hit the end of the stack before a null. So as far as like when you're actually creating your format, you want to try to use predictable values memory to actually help you. And there is a qualifier, the star qualifier, that you can use to print a large number of characters. And so in the example we see here, we have %*d, %n. And then the parameters we've passed, we have FFF, FFF, 1, 2, 3, and then the address of I. So the star in this case is going to print, FFF, FFF number of characters, and then it's going to print the 1, 2, 3, and then it's going to write the result to I. And so if we look at what was actually printed out, you can see that there's a bunch of blank space. You see the 1, 2, 3, and then you see the I value gets the value there. So this is a handy trick because this, again, can keep your string fairly compact. And again, if your format string is on the stack, you can use it. Lowland addresses are going to be harder to generate just because, as we talked in previous lectures, you have null bytes, and you can't have null bytes in your format string. So one of the things we can do with lowland addresses, however, is we can hide these using their negative value. And so if you look at what we see in the example down here below, we've used a -5, and the star qualifier with the negative essentially is going to left justify. And you can see that in the output over here, where you have the 1, 2, 3. You know, in the previous example where we had a positive value, you had all those space characters essentially. Then you saw the 1, 2, 3. In this case, the -5, and then but the 1, 2, 3 is left justified, but our I value is still receives 5 in terms of the number of characters printed. Another thing to take into account is that we're not actually limited to 4-byte alignments, at least on x86 platforms. So the %n, the address %n uses, turns out, is actually byte aligned. And so in this example, we've written hex 4141 or 41414141 crossing a D-word boundary, as you can see there in the right side of your screen. So you can see how these have changed. And actually, the red boxes here are off. Those should actually be shifted down 1. But if you look, starting at address 12FF80, you can see the 4141, and then on the next line, the 12FF84. You also see on the second half of the other 2 41s. So I'll need to update this slide to correct this error. On Linux, which this feature isn't implemented, but on Linux you can actually have this direct parameter access by using the this $ character. So %3 $x, what that will do is that will actually grab the third parameter. And so the benefit of this is going to make our formatting strings very compact, which is a good thing. So as an example, this first part where you see the .621786x and that long string, this is what you'd have to do if you wanted to write 0012FFC0 to the 200th parameter. You'd have to have this long string, which is totaling 816 characters. But by using this direct parameter access mechanism, we can actually reduce this to 24 characters using the string, as you see there. And we're able to just directly say the 200 parameter and then write that. So definitely a nice little handy trick that if the target system is Linux, that you can use. So a few limitations just to be aware of on Windows is that there are, depending on your operating system, there's some maximum numbers. And so here again, we're just covering up through XP. We're not getting into all the newer operating systems. But Windows 2000 actually lets you have fairly large values. NT 4.0 and XP, you have the 516x maximum. Now, in all of these, they typically are storing the fully expanded format string on the stack. And so the thing you have to be concerned about is that if you have very long format strings, there's a good chance you're going to overflow the stack and the program's going to crash. The other limitation, as we mentioned before on the last slide, is that with Windows you don't have the direct parameter access like you have in Linux, and so you really have to be concerned with your parameter alignment and the size of your string. So when you're building up the correct value to write out to memory. So this is just a little format formula that will hopefully be of use to you. So first is this called a math seed. So some large number that we can embed for the star qualifier. Then you have a series of the percent p's. And so the goal here is just to align the current parameter to our math seed. And so then you can use the percent star p to use that seed on the stack to boost our math. And then you have a series of percent p's to align the current parameter to the address. The percent n or percent hn, again, this is going to be the number of printed characters, and we want that to be the address of our NOP sled. The NOP sled can be, of course, expanded so that we have to align to the address we want. And then at the end you have your overwrite address. And so this is the value of what you want your target function pointer to be, because ultimately you want to have this call into your NOP sled. So just to kind of summarize some of the capabilities that you can do with a format string attack, perhaps the simplest one is just a denial of service, where you're just trying to crash the service with a bunch of %ns. Memory disclosure, we talked about that. The goal here is to try to leak protected information, and this is also a precursor to defeat other code execution protections. And typically a memory disclosure combined with another vulnerability will let you exploit the system on both, certainly on older systems, but as well as new modern day systems like Windows 7. You can use through the %n modifier, you can use this to help you gain arbitrary code execution. So since we can have arbitrary memory overwrites, then that gives us a variety of execution vectors possible. And you can also use these to bypass some sort of protection mechanism. So if you just think about corrupting memory, you can overwrite a format string to help bypass protections. So if you had some variable that was indicating 1 that you're authenticated, 0 means you're not authenticated, you could potentially use this type of attack to change that to your will, to indicate that you're authenticated or able to perform a particular function. And lastly, in terms of what are you actually trying to do, what are your targets for your format string attacks? This list should look fairly familiar to the list you saw when we talked about stack and heap overflows. Essentially, any of the control pointers that's going to help you gain execution. So virtual function pointers, return, exception handlers, C libraries, function pointers. Any of these would be good targets for a format string attack. And then as far as data goes, just any of the variables that you care to actually modify and want to use. You can do that as well. And that's it. So if you want to learn more about format string attacks, there's a lot of good references online that might go into a little bit more depth. The Shellcoder's Handbook has a nice chapter talks about format string bugs. But again, as with the stack and heap overflows and other lectures, the best way to familiarize yourself is to try writing up a few sample programs and play around with the different format specifiers to see if you can see both what the normal expected behavior is if you haven't used them before, but also try to misuse them and see if you can use those to leak information or potentially gain code execution. And that concludes the lecture. Thank you.